Hi, everyone. Thanks for joining me today for section number 3, where we're still talking about statistics, and today we're going to compare some different populations. Today what we're going to do is we're going to look at a couple different types of data, and we're going to look and see is our data, how it's distributed. And we're going to do that a couple different ways, one using some box and whisker plots right here. And then you'll also see us comparing data using some dot plots here. This section tends to be a little bit tricky for students. I'm just going to give you that warning right away. But I think it's because it's so vocabulary intense. So you might want to take a second and really think about some of these vocab words that we're going to talk about today while I'm going through them. Okay. So for our learning target today, it says, I can explain how to find the measures of center, so in other words, the middle, and variation, so how much our data varies, of a data set. First, here it says, use the mean and the mean absolute deviation to compare two populations when distributions are symmetric. Okay, so symmetric data, we use mean, or in other words, the average, and mean absolute deviation. So how much our data varies from the average. Okay, that's when we're talking about symmetric data. All right, oftentimes symmetric data, like if I were to show a symmetric data with a dot plot, it would show the bell-shaped curve. It would follow kind of that pattern. Or if it was a box and whisker plot, your whiskers would be about the same length, and your median would be in the middle, smack dab middle of your box. This would show symmetric data. These are two examples of symmetric data. Right? Now, on the other hand, sometimes your data won't be symmetric, and when it's not, when your data is skewed, we use the median and the interquartile range. Okay, so an example of skewed data would be like if one whisker on your box and whisker plot was really short and your median was not really in the center of your box and whisker plot, and the other whisker was like really long, this would be skewed. Or like if your dot plot showed something like this, where most of your data is here and you had little data here. Those would be examples of skewed data, where it's, you have more data on, or bigger numbers on one end compared to the other. And for that, you'd use median and interquartile range. So let's take a look at an example and kind of see if we can put some meaning to these vocab words. Example 1 says, compare the populations. Two data sets contain an equal number of values. So we have data set A in blue and data set B in red. The double box and whisker plot represents the values in the data sets. Okay, so it looks like for data set B and A, my smallest number is 20. My biggest number for data set B is 110, 130 for data set A. My median is 60 for data set A. My median for data set B is 90. Okay, so that's just a couple things you can quickly tell by looking at this box and whisker plot. Letter A says compare the data sets using measures of center and variation. So the very first thing we have to do is we have to decide, are we going to use the mean for the measure of center? So are we going to use the average, or are we going to use the median? Well, we have to look and see, is this data symmetric or is it skewed? Okay, well, just looking at these two box and whisker plots right here, I can see there's this big, huge whisker right here and a tiny one right here. And it's kind of the opposite in data set A. It's not very even. So right away, I'm going to determine that the first thing I'm going to do is I'm going to say this is skewed. It's not symmetric. Okay, so therefore, when I have data sets that are skewed, distributions that are skewed, I'm going to use the median, and I'm going to use the interquartile range. Okay, just like it said up here. When they're skewed, use median and interquartile range. Okay, so I have to do that for both data set A. I should have color coded here. So this is data set A. And then I also have data set B that I'm going to need to look at here. So I'll have the median and the interquartile range for both sets of data. And then I can kind of compare them. Okay, so let's look and see here. What is the median of the data set A? Well, the median is that middle line in the box and whisker plot. So the median for letter A is 60. And the median for letter B, middle of the box and whisker plot, is 90. The interquartile range, remember, the interquartile range is the box, the inside of the box. So you take the higher value of your box and you subtract it from the lower value. So that's, I'm just going to say your box range. Might be a good way to remember that. So that means I'd have to take 100 minus 80, which would give me 20 for the interquartile range for data set B. For data set A, it would be 80 minus 30, which would give me 50 for the interquartile range for data set A. Okay, and let's remember here, this is a really good point that this light bulb gives us. In a box and whisker plot, about 1/4 of the data are in each whisker. So this is 1/4 of the data. This is 1/4 of the data. And then about half of your data is inside the box and whisker plot. So this represents 25%. This represents 25%. And then this, your box, represents 50%. For a total of 100%, right? So that's kind of a good reminder, and you'll see that here in just a second with one of these other questions. So when we compare the measures of center and variation, I'm going to say that I'm just going to make a statement here for kind of my final answer. I'm going to say, so data set B right here has a greater measure of center. In other words, it has the greater median, right? 90 is bigger than 60. And data set A has the greater measure of variation, right? Our measure of variation is the interquartile range. So this one's 50, this one's 20. So I'm just comparing those, right? Letter B says, which data set is more likely to contain a value of 95? Which data set is more likely to contain a value of 95? Well, if you look at 95, that would be right here. You can see that on data set A, that falls in one of the whiskers. So about 25% of the data values in A, I'm just going to put in A like that, are between, let's see what this whisker is. It's between 80 and 130. Okay. If I look at B, I can say that about, well, notice that 95 falls in the box. And remember, In the box itself, about half the data is in the box. So about 50% of the data in letter B are between, let's see, our box is between 80 and 100. Okay? So which one of these is more likely to contain the value of 95? Well, this only represents 25% of the data. This represents 50% of the data. You can see our box is inside where that 95 passes through. So data B is definitely more likely to contain a value of 95 because 50% of our data is in there and only 25 in this whisker for the data set A. And lastly, letter C asks, which data set is more likely to contain a value that differs from the center by at least 30? That differs from the center by at least 30. Okay, so what we're going to look for here is we're going to look at the interquartile range. So this letter A has its interquartile range spans from 80 all the way to 30. So that range is 50. The range of letter B goes from 80 to 100, which is only 20. So which one is more likely to contain a value that differs by at least 30? Well, that's definitely data set A. Okay, and that's because the interquartile range is a lot larger, and that's what it's asking for. Which one is more likely to differ from the center by 30? Okay. All right, go ahead and check out the two triad problems here. I'll have you pause the video now to try these two and then come back to see if you got them right. Letter A says, which data set is more likely to contain a value of 70? All right. Well, you can see here for data set B, it's a whisker that's in the 70 point. That's only 25% of the data. But for data set A, the box is in that 70. So that would be 50% of the data. So that would definitely be data set A. And number two is, which data set is more likely to contain a value that differs from the center by no more than 3? So here we are. No more than 3. We're looking for the small or the smaller IQR, and that's definitely data set B. Data set B had the interquartile range of 20 versus A had 50. Okay. All right, let's move on to the next example. For example 2, it says describing visual overlap. So where these two data sets kind of overlap. It says less visual overlap indicates more significant difference in the measures of center or the medians, right? The more that these are overlapped, the closer that their medians are going to be. If all of our data was spread out over here on data set A and data set B, all of our data was over here, their medians would be very different. But the closer that they get to one another, the closer their medians are going to be, or their middle numbers are going to be. That's kind of what this is saying. Okay. When two populations have similar variabilities, the visual overlap of the data can be described by writing the difference in the measures of center as a multiple of the measure of variation. Greater values indicate less visual overlap. Okay, kind of like what I just showed you. All right, it says the double dot plot shows two data sets, A and B. Express the difference in the measures of center. So we're still working with that measures of center. So I'm still thinking I got to use the mean or the median, one of the two, as a multiple of the measure of variation. So that means I have to use the MAD, or the mean absolute deviation, or the interquartile range, depending on if my data symmetric or is it skewed. Okay. So that's, again, the first thing that I'm going to determine, is my data symmetric or skewed. Well, if I look at A, man, that follows that bell-shaped curve real nice. That's definitely symmetric. And data set B is pretty close. If I just were to take out this point right here, you could see that it is 2 and 2, 1 and 1, 2 and 2, and then in the middle here. So this follows that curve pretty well. That's awfully symmetric as well too. So I'm going to say that my data is symmetric. Oops, I spelled symmetric wrong. It's Y-M-M-E-T-R-I-C. So my data is very symmetric. That means I'm going to use the mean or the average and the mean absolute deviation for my measure of center and measure of variation. Okay, so what I need to do then is I first need to find my mean. Okay, I need to find my average. So to do that, I need to add all my numbers together and divide by how many there are. So I'm just going to count first to see how many data points I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15 different points. I'll add up my total here. So I'll take 20, and I'm just going to use a calculator for this, guys. So if you have one handy, feel free to punch it in. 20 plus 30 plus 30 plus 40 plus 40 plus 50 plus 50 plus 50 plus 60 plus 60 plus 60 plus 70 plus 80 plus 80 plus 90. And when I do that, when I punch that into my calculator, I get 810. Okay, so to find the average, I'll take that total and I'll divide it by the number of entry points, which is 15, and that'll give me a mean or an average of 54. Okay, and does it look like it's about 54? The average is about 54? Well, actually, yeah, it looks like the bulk of my data is right here. I would definitely consider that the average. And look at that's right between 50 and 60, which 54 is really close to that. So just visually looking at it, that looks like it makes sense. Okay, let's do the same for data set B. Let's find the mean for data set B. Again, I have 15 data points, and I just need to add 0, 0, 0, 10, 20, 20, 30, 30, 30, 30, 40, 40, 50, 60, 60. And looking at this, I bet you can tell that the average looks like it's going to be a little bit smaller than data set A. It's a little bit more to the left. When you add those numbers up, you get 420. Divide that by 15, you get a total of 28 for an average for this data set. And look at there. It does look like it's really close to 30 for our average. Okay. So I found my measures of center. I found my means. Next, I need to find my mean absolute deviation, or my MAD. Okay, this goes back to let's see, 6th grade. And if you don't remember how to find the mean absolute deviation, that's okay. But you might want to go back and check out some Khan Academies on how to find that. Okay, what the mean absolute deviation means is how much does each point differ from the average. Okay, so for example, my first point is 20. How much does 20, how far away is that from 54? Well, that's 34 away from 54. Plus, how far away is 30 from 54? Well, it's 24 away. And I have 2 of those points, so plus 24. Plus, how far away is 40 from 54? Well, it's 14 away. And I have 2 of those. How far away is 50 from 54? Well, it's only 4 away, and I have 3 of those. So 1, 2, 3 4s. I'm sure you're starting to get the idea, right? How far is 60 away from 54? Well, it's 6 away, and I have 3 of those. And then once I find that number, I have to divide that by how many data sets, just like I did for my mean. So I know it's 15. Okay, how much does 70 differ from 54? Okay, well, 16, 80, 26, and I have two of those, and 90, okay, 36 away. When I add those numbers together, plug and chug on the calculator, I should get 244. When I take 244 and I divide it by 15, that gives me 16 for the mean absolute deviation. What does that mean? That means that on average, the other points differ from my mean or my average by 16. On average, they're 16 away from the mean. Okay, so if I were to repeat that process for data set B, to find the mean absolute deviation for B again, it's going to be divided by 15 and finding the average of how far away my data points are from the average. Well, my average is 28. So how far away is 0 from 28? Well, it's 28 away. So 28 plus 28 plus 28 plus, this is 18 away, plus 8 plus 8 plus 2 plus 2 plus 2 plus 2, right? You're adding all these up. And when you do that, you should get 236. We're finding the average of that, so divide by 15 and you'll get 16. Okay, so the mean absolute deviation is 16, or close to it. It's about 16 for both of these data points. Okay. Now, so we found our mean and our MAD for both sets of data. It wants to know, it says, express the difference in the means as a multiple of the measure of variation. So what that means, and I'm going to highly recommend you write this down. It's kind of hard to go through this jibber jabber. Is it you have to find the difference in your means. So in other words, we have to subtract our means, and we have to divide that by, because it wants it as a multiple of the measure of variation, we have to divide that by our MAD. So what's the difference in our means? What's 54 minus 28? Well, that'd be 26, divided by the mean absolute deviation, which we found was 16. 26 divided by 16 would give you about 1.6. So what does that mean? That means that the difference in the average, or the averages, is about 1.6 times the mean absolute deviation. Okay, so that's kind of a lot to throw at you, but that number, you can kind of start to see it says less visual overlap indicates more significant difference in the measure of center. So here we had, they were relatively close. So you can see that there's not too much of a difference there. Greater values indicate less visual overlap. Okay, and we didn't have that in this case. All right, pause the video now to try number 3 here. Triad 3 says, what if each value in the data plot for data set A increased by 30? Okay, how does this affect your answer? And explain. Okay, so if you were to do that, it might take a little time to do that. What would happen is the mean increases by 30. Right? So that would mean that would change this to 84. It increased that by 30. Right? The MAD does not change. That stays the same. If each point changes the same amount, then that doesn't change that at all. So data set A still has the greater mean time. Right? The difference in the means is now 3.5 times the MAD. So if you were to recalculate this out, right, you'd have to take 84 minus 28 divided by 16, which would give you 3.5. okay, times the MAD. So this new number now would become 3.5 when you change or increase it by 30. So the number is greater, indicating less overlap in the data. Okay, I'm going to write that down. The number is greater, right? 3.5 is greater than 1.6, indicating less overlap in the data. And that makes sense. If all of this were to shift to the right by 30, right, there would be a lot less of these numbers that would overlap. If we shifted just a little bit more to the left, you'd have almost all overlap. The data points would be very similar. All right, hopefully that's making sense. I know that was kind of a doozy, kind of a long problem. Stick with me here. We got one more to go. All right, example 3 says the double box and whisker plot represents the heights of roller coasters at 2 amusement parks. Okay, so here's Park A, Park B. Are the roller coasters significantly taller at one park than at the other park? Okay, so first thing, like I've done before, is I'm going to say, is my data skewed or is it symmetric? Well, for A, it's definitely skewed. It's got this longer whisker. For B, it's not skewed, but for A, it is. So I'm going to say it's skewed. And so I'm going to say, I'm going to use the median and the interquartile range for both Park A and Park B. Okay, we can quickly look and see. This is what's kind of nice about box and whisker plots. Our median is at 50. And our interquartile range, 55 minus 45 is 10. Right, the ends of the box subtracted from each other. The median for Park B is at 55. And the interquartile range, 60 minus 50 is 10 again. Okay. So because the variabilities are similar, right? The interquartile ranges or the variabilities are similar, you can describe the visual overlap by expressing the difference in the medians as a multiple of the interquartile range. So similar to what we just did, we're going to find the difference in the medians, and we're going to divide that by our interquartile range. Well, what's the difference in our medians here? What's the difference between 55 and 50? Well, that's just 5 divided by the interquartile range, which is 10, which gives us a half, or 0.5. And because that answer is less than 2, the difference in the medians is not really significant, right? There's not, you can see just by looking at it, we have quite a bit of overlap here, right? They have very similar heights in our data. You can see that this number is small, so that means our overlap, we have a lot of overlap or similar data. One is not really like a whole lot taller than the other one. Okay, so I'm just going to say that. The roller coasters are not significantly taller at one park compared to the other one. Right? If Park A had the box and whisker plot like all the way over here, then we could say definitely, like, yeah, this one is, Park A is a lot taller than Park B, but that's not really the case. 50% of Park B is actually greater height than 50% of Park A, but Park A has the taller of the two, right? Their tallest roller coaster is 70 meters compared to Park B's only 65. So it's kind of a wash. We got a lot of overlap, a lot of similarities. There's not one that's significantly taller than the other. Okay. All right. I'm tired of blabbing at you. I'm sure this lesson was kind of a mouthful and kind of a lot of information to take in, but hopefully you can take something away from it and be able to compare different populations here using box and whisker plots and dot plots. And let me know if you have more questions. I know when I first learned this, I did too. So thanks for checking this tutorial out, and I'll see you guys next time.